Alright, kiddos, so I had you guys taking chapter 5.1, just start taking the notes. So anybody who's gone, you might want to go ahead and pause and write down that page of notes just to get ready, because we're going to go fast once we get there. But right now in the back of your spirals, integration as net change practice. Ready, set, and go. You may work in your groups, you may collaborate. And you may use your, look at those decimals, calculator. And you may use your, look at those decimals, calculator. This would be a calculator problem.
The rate of growth is
This would be a calculator problem.
No, you just put it, so this 1970 is year zero, so it's not going to be right? Yeah, we just do the integral from 0 to 20 years.
Oh, you would go on right?
And then just add 125 because that's your initial. So what's that?
We're going to add it today.
0.6. So it's
20.
1990 is
Did you do that definite integral already, Bert?
I am just adding and
wait, you're forgetting something.
5, 0,
Wait, how did you get 125?
Okay.
That's like P of 20. Isn't it F of, I guess, yeah, just 120. 3 of 0.
You get really good.
Oh, wait,
You
what's...
get less.
it's just P of 20 at the end.
It's because 0 is 19.
Oh, so it's P of 20 is equal to 125 plus.
The initial population. That's basically it. Wait, is that in thousands?
because it's the opposite.
That's what I got.
Okay.
Alright, you guys are still working.
Oh.
Okay, we have all the important information written down, right? All the important information written down? Take a second. I'm going to switch the screen in 1 second to HCTV, so I want you guys to make sure you have all the important information written down. You can ponder a little bit longer. I did say you're allowed to use your calculator. We'll see if you guys know what that means, because we are going to go over the worksheet and make sure you guys know which problems are calculator problems and talk about logistics. But let me pause this real quick. We'll come back to it in a second and watch HCT just a second ago. So right here on your notes, you guys see that I have uploaded the Chapter 4B Integration as Net Change packet. Now this is just the blank packet, true?
Yeah.
Okay, have you guys been working on this blank packet? Yes, in just a moment we're actually going to go through this blank packet and see which problems are calculator problems. I'm kind of proving a point this morning with the example that we started off with about how to use your calculator properly. Maybe some of you guys are, maybe some of you guys aren't. But we're going to go ahead and go through and make sure you guys know which problems are calculator problems in just a second. But also, tomorrow, I'm not going to be here. I'm going to be gone the entire day. And that should be the last of the weirdness of me not being here. But coming back, since I am not here, let me fill you guys in really quickly with what's going to be going on, what I'm telling the sub. I'm basically telling the sub to let you guys do your thing. Meaning, get out that integration as net change worksheet, which is probably not done. Anybody have it all the way done? Completely confident that's right? Exactly. So, you can work in your groups on the worksheet. However, listen carefully. I'm also going to have or tell them to let one of you guys log in to go on my website to get into the class folder. And guess what else is going to be here besides the worksheet? The key. Now, the key is going to be kind of awkward. I can even show it to you. I think it's right here pretty close, really fast. It's going to be kind of awkward because it's handwritten. Ugh! Nasty, I know. I just haven't had time to actually make my own key for this. Nice thing is, it's actually another calculus teacher who made the packet, and I just loved his organization and his inclusion of AP questions, etc. So I've kind of stolen it for a few years now. These are his answers, okay? Is it nasty? Yes. Is it numbered? Yes. Are the answers boxed? Yes. Is it AP accurate? Yes. So I'm going to have one of you guys, that's going to be loaded in your drive tomorrow morning for the purpose of you guys still having another night to add a little bit to it, to come tomorrow with what you haven't been able to attempt or get or understand. As a class, look at the answers, whatever ones you have been able to work on those you haven't been able to work on. And then you're going over two things. One, what haven't we attempted yet? Keep working on it. Two, what have we attempted and gotten wrong? Let's figure out how to do it right. Does that make sense? Then on Monday, what do you think I'm going to ask when you guys first come in after we watch HCTV and pray?
Any questions?
Questions. What don't you get from the packet? You've already seen it, attempted it, graded it, and worked together on a class on the questions that you had, and then maybe over the weekend finished attempting it, grading it. So then what questions do you have as to why the answer is what it is? Why is it very helpful, and why do I try really hard to make sure that most of the time when you do your calculus, you have answers available?
Because you won't know if you're wrong.
You won't know if you're wrong unless you know the answer. But then second of all, once you figure out you're wrong, I want to give you guys time to see if you can fix it on your own and understand why, and then come to me with the, okay, I've tried it, I've graded it, I'm still stuck on, let's talk about it. Does that make sense? Okay, it just simplifies the process as long as you guys let the process work. Meaning, you got to try it first. Then grade it. Then ask questions about what you still don't understand after you look at the grading and say, okay, hold on, go back to the concept. Does this make sense? What did I do wrong? I still don't know. Okay, let me know that on Monday. Sound good? Okay. So we're good with what we're doing tomorrow? Grab it out the packet. Working in groups on things that you're stuck on. What you have been able to attempt, the grade or the answer key will be up here. I mean, you guys will have to maybe like scroll back and forth, but if some of you or one of you, Sean, do you mind just being the one to log in? Okay, you're going to log in, get the answer key up on the screen, and then if you guys don't mind, you know that the smartboard is touch sensitive, you can come up and scroll to the one you want to see. Is that okay? And then if someone else has, oh, I want to see something, give a second for the person to grade, and then maybe, Sean, you could even like kind of quickly scroll through and let people see the multiple choice answers, because most everyone will have attempted that, and then get to the FRQs and you guys can look at it. If the sub doesn't mind, I'll put it in there. I don't mind you guys getting on your phones and looking at the answer key as well, as long as you don't abuse the privilege. You got it? None of this like snapping during class being like, oh, hey, look out. Yeah, no. But if you're getting the answer key and you're checking, I just use Snap because that's the one that we use a lot, right? Anyway, True, yeah. Or we're like chatting about like how we're not doing work and we're supposed to be. Anyway, go team. Are we good for tomorrow? Cool. So weekend's homework is going to be finishing this up. So what are we doing today? Not that, because you're able to do that without me. You need me for, I would at least hope that you somewhat need me for, Chapter 5, which we are starting today. Don't worry, we're coming back to this problem. Don't open your notes yet. Stay in your homework files. What we're doing today is getting a big introduction to 5.1. You don't need to start 5.1 this weekend. If you would like to, that's okay. On Monday, we're going to have a work day on 5.1 with worksheets that I'm going to get printed off in the office. I don't have quite done yet because I've just been playing catch up all week. But 5.1 we're going to really get into on Monday. So today we're laying the framework, the groundwork, the foundation, whatever. We're laying the beginning of this section, and then on Monday we'll dig into the AP stuff that will help us practice. Does that make sense? Okay. So let's come back really quickly to integration as net change. The last thing I want to talk about, besides going back to the packet and really quickly having you guys write down which problems are calculator or no calculator, P.S. get out your packet and have it ready so you can mark down calculator, no calculator on the problems. This one. Kiddos, why is it integration as net change? ¿Por qué, pourquoi, how come?
Because we want the final.
They want the final population. Do we care that it's population? No. Could it be water? Yes. Could it be snow? Yes. Could it be bananas? Sure. Could it be the temperature of a potato? Sure. Could it be the temperature of biscuits? Sure. I don't care. But we want a final amount. Does that make sense? Okay. So final amount. The final amount is after how much time has passed?
About 20 years.
20 years has passed. So can we say that we want P, and I'm using P because they use P. I'm like, whatever, okay, fine. P of 20, is that what we want?
Yeah.
We want the population after 20 years has passed. Okay, why is this integration has not changed? It doesn't have to be, but this one is. How come?
Because
Find the final.
for the final we need an initial.
We need the initial, where it started from, which would be P of, now pause, what did they give you? Do they give you 0? Do they give you 5? Do they give you 10? What do they give you? Population at?
P is 0.
Okay, 1970, we can make year 0. Does that make sense? Wait, hold on, pause. The rate of growth T years later. Then what? Then 1970. So when T equals 1, what year are we talking about? 1 year later, 1971. When T is 5, what are we talking about? 5 years later, 1975. So what is 1970? Year 0. You guys are totally right. Good.
That's 4 years. Good job.
Now what do we do?
Now we want to find that change.
Because we got to find the change. And the change, well, we don't have P, we have P prime. What can we do with that guy to find the change?
Let's integrate her.
Go from 0 to 20 of P prime of T. Wait, why didn't I write the entire equation?
Because you don't have
If this was an FRQ long answer, I just told them who I'm about to put into my What? Put into your calculator.
Well, that's
If you did any math besides writing this down, I feel so sorry for you. Not because it was ridiculous what you did. If you started anti-deriving, good job. I'm proud of you for the math that you know how to do. But if this is a calculator problem, there will be absolutely no work shown on the answer key. No points given for work shown. All that wasted time. Because all you would need to do is the following. What is P of 0?
125.
What are they saying to add it to?
Yeah.
Hey, P.S. You can go find the integral that way, or isn't there this really nifty shortcut? I think it's alpha. Oh, hold on. I need to get my cursor in the right place. There's a shortcut for an integral, alpha window, I think. F function integrate number 4. Tyler, go ahead.
Would this be like a problem on the FRQs with no calculator?
It could be. But frequently they give you this when they give you a nasty function, and a nasty function you'd be able to plug into your calculator. But you would need to write this line because they would give you a point for showing what you're going to do, and then all they would give you a point for is actually doing it. So I have 8, struggle. Second insert plus. But they would give you absolutely no work. If this was a calculator problem, absolutely no points for any work that you do. So any work you do is wasting time, number 1, and it's possibly making it wrong, number 2, which would be so sad. 0.3 t squared. Guys, do we like problems that say use your calculator?
0.03.
Yeah, because all you gotta do is say, oh, hey, look.
It's 0.03, not 0.3.
Oh, thank you. This calculator takes so long, and I just get distracted and I write things down. Gracias.
I have to do second insert. Oh.
That's a lot better than typing and having to retype.
Well, yeah, but it's.
Okay, now we're good?
Yeah.
Makes a lot more sense, too. Guys, does it make sense in 20 years to go from 125,000 to 1,185?
Unlikely. Very unlikely.
It's kind of weird.
Maybe if there's
It is possible.
extra good grain that year. It's Alaska, so.
Pause. Should I just box 465 and be like, I'll know what I mean?
No.
No. Thousands. Don't write thousands, just, I mean, in the sense of don't put like 000, but you can use the unit that they use. 465 thousands. Okay. Final equals initial plus change, and change, if you do not have a function for population and you have a function for rate, you integrate. Okay, let's go look at that worksheet packet, because if there are any other calculator problems, do you have to solve it the long way? No. If I can find your, there we go. That's not it.
Let's see it.
Donde está Chrome? There it is. Okay, let's get rid of that. Let's go here. Let's go there. Let's go here. Okay, integration, does that change? Number 1. I guess you can use a calculator. There's not really a lot of point to it. Yes. Hey guys, Do you need to integrate on this one?
No. What could you for us?
Do you need to think of the idea of an antiderivative or an integral or area?
Yeah.
Yes. So you do need to integrate. The problem is, do they give you a function for gallons per hour to get to gallons? No. So since they didn't give you a function, how are we going to integrate? Well,
By looking at approximations.
approximating the area under. Did anybody figure out what the area of one little square is, or rectangle, I should say? It's 6 by 50, which would be 300. So figure out how many squares you think approximately is here, and you might need to do like half a one and then half a one, and maybe that's like 2/3. And anyway, approximately how many squares multiplied by 6 by 50 by 300, and there you go. Anyway, number 2, that's a trapezoidal approximation. I guess that could be calculator. Yeah, number 2, go ahead and put C for calculator. We're only going to mark the calculator ones, okay? Number 2, I guess you could put a C. I don't think it's a big deal. Number 3, C. It's a calculator one. Because it says round to the nearest, that's decimals. Yeah, number 3 is C. Number 4 is C. Number 5 is not. You cannot use a calculator for that. You're just showing what it looks like. Number 6.
Yeah, for these ones,
Yeah,
I think
you need her.
Yeah, number 6
No, you don't
is.
actually.
Yeah, I don't think you.
Well, okay, well,
Yeah, you do down here. Hold on, wait.
You don't if you do a
Nearest set, that's definitely not nearest set, that's definitely calculated. 6 is a C. I'm not saying you need it for every single part, but yes, 6 is a C. Number 7 is definitely a C. 7 is a calculator. Now guys, hold on. Pause. In our notes just a second ago with that practice problem, did I just write the number? No. For long answer for FRQs, write this line. Explain what you're doing, but you have to literally like plug in every single, put the function in. No. Show them what you're doing, go to your calculator and do it and say, here's my answer. Okay? I apologize. We were on number 8 looking at, right?
Yeah.
Number 8, no. Oh. Go ahead and put a C. Yeah, put a C. Put a calculator.
Yay.
Number 9 is a C. Is a calculator. Number 10 is a C. Is a calculator. Number 11 is a C. Number 12 is a C. Kiddos, can I show you something really quick? Look up here at the very beginning. Do you see how it says AP 2011 number 2?
Yeah.
AP, from the AP exam, the actual given AP exam that year. 2011, the year that it was given. Number 2, the second in the series of 6. Do you notice what's true about all of these?
They're all good.
We're all second question.
That's weird.
Now, are all these questions exactly the same? No. But are they all similar? In a sense of needing some sort of integration, word problem application. Anyway, just an idea. Now, is it always, I'm not trying to tell you that there's like this magical pattern to the APs, but what I am trying to say is our calculus, what we've been learning, is definitely going to be applicable in that AP exam. All right, cool kids. You have an idea for what we're doing tomorrow, right?
Yes.
Cool. And you understand what I mean by calculator, when you can use it, and what benefit it can give? Cool. You guys, when you grade tomorrow, make sure that you grade in color pen. You know what to do. Grade in color pen. But if you get something wrong, don't just give up and say, oh, I'll ask Miss D on Monday. Work through it. Persevere through it. Talk to your classmates about it. Raise your hand and be like, hey, how do I? And let's figure it out. Doesn't mean you have to have all your questions answered by Monday, but I would like you guys to have at least gotten as far as possible. For those of you guys that are trying to find these notes, P.S. the integration as net change notes I have put at the end of chapter 4B, because remember that's still the chapter that we're in. So that's exactly where I'm saving this now if you do need to go back and access it. But you guys also know you can go on the video and just pause and get it that way. You guys have multiple ways to get the stuff that we cover in class. Let me go ahead and export this real fast so that we have it ready for our website. Today I should be here until about 4-ish. If there is something you need to talk to me about during lunch or after school, period 7, I might be a little busy, but you can try me. Here we go. All right, chapter 5. Slope fields. My computer's been kind of weird and funky, so I'm trying to close this file down so it doesn't freeze. There we go. There we go. All right, number 5. Chapter 5. Slope fields. What do you guys think slope fields are about?
Slopes.
Fields of slopes. Question. When we talk about slopes in calculus, what are we usually referring to? Derivatives. I totally agree. Usually, we're talking about derivatives. Derivatives. Wait a minute. Hold on. But how do we see derivatives, like on a graph? How do we see slopes? How do we picture slopes? How do we think about slopes? Tangent lines. Okay, so slopes, derivatives, tangent lines, a field of tangent lines? Doesn't that just sound awkward? Think about it. A field. You guys think about like a minefield. Anybody ever played Minesweeper? That's an old game.
Oh,
Yes.
I never liked that.
Oh, it's so good.
Not Minecraft.
Minecraft.
Minesweeper.
Minecraft is the...
Minesweeper was an old school game. It was one of two. There was Solitaire and there was Minesweeper on the very first like personal computers that were coming home.
It was fun.
I remember when my family first got a computer and it had Minesweeper. I know it sounds really weird and awkward to you guys, but it had Minesweeper, it had Solitaire. Minefields. Minefields. If we were trying to map a field of mines, you guys can kind of think of like it'd be a coordinate system, right?
Yeah.
And we try to like think about it from some reference point, how far and how far over and up or back and down in order to get to the different mines and they'd be plotted, right? So I want you to think of a field being plotted on like an X and Y axis. Now, if I was to say a field of slopes, a field of tangent lines, why does that sound really messy? Yeah, they're going to go on forever. And so if you have like different slopes, then you're going to have a line here, and then a line there, and then a line there, and they're all going to intersect. Ugh. The idea is how good or for how long is a tangent line a good approximation of a curve? Just think of some sort of curve like a parabola, and think of a random point on it, and skim, do a tangent line. It's only good for how long?
1 point.
1 point, it's only perfect, and then kind of close for a little while, but then what's it going to soon do for any curve?
Really
It's going to diverge. It's going to get farther and farther away, right? So I technically need the whole tangent line if it's only really good for a little bit. So I want you to think of field, lots of different points. Slopes of some sort of curve. We're not looking at the curve itself. We're actually looking at the little slopes. And just cutting them down to be little baby tangents. Slope fields, fields of little baby tangents. Little baby tangents to who? I don't know, some sort of function that's been given to me. But wait, if we're looking at the slopes of somebody, maybe we're needing to look at a differential equation. Real quick, differential equation, put in parentheses. What I mean by that is dy dx equals. In chapter 4a and 4b, we were dealing with being given derivatives. Now, sometimes they were given in an integral, so we didn't really think about it. It was just like, oh, hey, it's the integrand. Let's go. But whenever we get to word problems, we have to think about if we're integrating something, we're going backwards from. Usually it's from a rate back to an original. Usually, not always. Every now and then they have us integrate an original for like an average value, which is kind of awkward and weird. I think one of your FRQs does that. It's the one with H and temperature, I think. You're integrating H and it's awkward because it's not a rate. You're like, what is this thing? But it's an average value of H. Anyway, in section 5, or chapter 5, section 1, they're going to give us a derivative. They're going to give us a differential equation. And this thing called a slope field is going to allow us to take this differential equation, make lots and lots and lots of little baby tangents from that, because tangents are determined by the slopes, which are determined by the derivative. Make lots and lots of baby tangents. And then from the baby tangents, be like, okay, if I put all these little baby tangents together, what's that curve that's going through? What's that curve that's going through? Now, first of all, before we even get to the field of slopes, let's get you used to the idea of a differential equation. We're not going to do really hard ones this year. There's a whole class in college called differential equations, DiffEQs. Where they deal with much more complicated ones than this. But the idea of a differential equation is it's some sort of equation that has some sort of derivative in it. Could be a first, could be a second, could be a third, could be a combination of the above. I would call this a first-ordered second order differential equation because there's a second derivative. If there was only a y prime, I'd call it a first ordered. So we put the order of the differential equation by the derivative that's in there. But you guys don't have to get all crazy. What I want you to realize is a differential equation is literally just using a derivative as part of the overall equality. So for this one, they're asking you to determine which of the functions is a solution. How can I see if sine works for that differential equation?
Okay, could we just like move y over and then just like derive twice and then be like, hey, does it equal like, you know, itself at the beginning, I guess?
Get the pieces, plug them in. What's negative sine of x minus sine of x?
N.
Not 0.
Exactly.
Right? So is he? No.
No.
What about this guy?
Okay.
What would y prime be?
Negative 4 e to the 4.
Because it's 4 e to the u times u prime, which is negative 1. What would y double prime be?
Factor 4 e to the negative.
Because it'd be negative 4 e to the u times u prime, negative 1. So when I go ahead and plug them in, what's going to happen if I do 4 e to the negative x minus 4 e to the negative x? Whoops. And then this one, whoops, turn it off. C, e to the x. Because this one, e to the u is just e to the x, right?
Yeah.
No. So who else is going to work? Because if I subtract that guy from that guy, yes, it equals 0. So homework might have something where it's just having you play around with differential equations and realize, like, hey, the big idea between differential equations is there's some relationship of the derivative with maybe other quantities. The problem is, what if we needed to get back to y equals to solve that differential equation? Maybe it's not possible. Maybe it is. But differential equations can get kind of complicated. It's not so easy as just having like, hey, y double prime is equal to this sort of function of x and you integrate twice. Sometimes it gets a bit more complicated, and even to be honest, there are some differential equations that we can't even solve by hand to get back to the original. This one, they just gave us a lot and we tested and said, oh, hey, here's some that work. However, we're not always going to be able to solve differential equations, and so sometimes the slope field is a way of dealing with ones that we can't solve. Real quick, general versus particular solution. General versus particular solution. The general solution for a differential equation is going to have the constant of integration is still unknown. So the c is still in there. Now, be careful. When the differential equations get a little bit trickier, it's not always plus c. It could be multiplied by c. It could be c in the power of. It just depends on the differential equations. We're always doing plus c when we integrate. The dilemma is, depending on how complicated the differential equation is, c might start getting inside a function. So you might not end up with always a plus c on the outside. Or maybe some of you realized that in the last example. All of a sudden, c was being multiplied. Is that a thing? It ended up this way. It was plus c originally, but it ended up that way. We'll see how, probably next week. But constant of integration, unknown. And a general solution to a differential equation is going to be a slope field. Remember how we talked about when we have plus c unknown for basic antiderivatives? How the functions would just be vertical translations of each other? If we had like x squared plus c or x cubed plus c, it could be plus 1 or plus 2 or plus 5 or minus 1, minus 5. They'd be vertical translations of each other. The slope field basically says, I'm not exactly sure where this curve is, but I know what it looks like, so let me show you kind of all the different possibilities. A particular solution is an actual established curve, and it's established by a particular point, which we sometimes call, well, I call a clue. They give you some sort of point that establishes it, that sets it, that we could plug in and solve for C. And in differential equations in general, a particular point we could call an initial value or an initial condition problem. As soon as they give you a point, all of a sudden it goes from all this ambiguity of, well, it could be any of these guys, to being like, no, it's this specific one. So general versus particular. One's established, one's unknown. We're not going to get to a lot more than this, guys, but I do want to at least show you what a slope field looks like if I can. Oh, struggle. There we go. These are slope fields. I just want to introduce the idea to you. We'll get back to this on Monday. We're going to have a packet we'll be playing with. And that's where these examples come from. We're going to kind of learn how to make it ourselves, but there are a lot of points here to make, so we're not going to make one probably this big. We'll make smaller ones. But the idea is, guys, at every point 0, 0, 1, 0, 1, 1, 1, 2, 1, 3, that point was plugged into the differential equation, the derivative was found, a slope was realized, and then it was sketched. Ooh, up 1 over 1, little baby tangent. Ooh, up 1 over 2, little baby tangent. Ooh, down 1 over 2, little baby tangent. And if you put all the little baby tangents together, the derivative gave us the little baby tangents, but it also points us to the antiderivatives curve that was in between, which is pretty cool because that means even if we can't solve a differential equation, we can still see what the antiderivative looks like. All right, cool kids, get out of here. You know what to do for tomorrow. If you have any questions about anything going on in today, and I'll see you guys later. Alligators. Bye.